All right, welcome everyone to COMM 191 review. My name is Evan. I'm here as part of UBC Simplified, which, little plug, it's this organization that we've started. The goal is to provide completely for free, forever for free, access to videos, materials, formulas, whatever it can to help you the best way that we can. So yeah, it's pretty cool. Anyways, with that out of the way, let's get to reviewing what is basically the entire course up until now that'll be covered on the midterm for stats. I entered this class hoping that I would be able to find out the probability of someone saying yes when I ask them out on a date. That has not happened yet, but hopefully by the end of the course, I'll be able to know what that statistic is. Okay, so let's starting off the two different types of data. One, we have categorical, the other we have quantitative. The biggest difference is one, you can take a meaningful average, and that's for quantitative data. So if you can take an average of that data and it makes sense, then that is quantitative data. There are some examples there, but the biggest thing to keep in mind is that it depends on the type of a question. Age could be quantitative if it's just like 64, 65, 66, or it could be categorical if it's between 50 and 55, between 56 and 60. So it's not necessarily, oh, ages are always quantitative or they're always categorical. It really depends on the question, and you can go from quantitative to categorical. So if you collect data through a quantitative means, you're able to translate that to categorical, as we just saw, but you can't take categorical data and translate it back into quantitative data. So it's a one-way street on that. There's a few other different types of data. These are more or less important. So the one thing to keep in mind is dates. They can be a mismatch of stuff. They can be strings. They can be categorical, or if it's like a specific time period, it could be quantitative. You have counts, which is just counting how many times something has happened. The one thing to keep in mind are identifiers. Those are a unique set in your data set, so they're basically used to identify each respondent, so they cannot overlap. So if you have, for example, like a team, that's not an identifier, like a football team, that's not an identifier because there could be multiple players on the same team. So it's a unique identifier in order to distinct different respondents on the survey. You can have, oh, do you agree with this on a scale of 1 to 5? That'll be kind of ordinal categorical data, or nominal, which has no distinct order for categorical data. Different types of kind of visualizing it. Cross-sectional, that is taken in a specific moment of time. So if you see words like on or at, those are identified with kind of cross-sectional data. So it's like on, or like through, like on October, this was identified, versus time series is over time. So across 10 years or across the year. You're looking over time to analyze trends, and I like to think of it as basically a collection of cross-sectional data. So your time series plot or your time series data, each one of those points is in itself cross-sectional. So you combine a bunch of cross-sectional data, boom, now you have time series data. Any questions up until this point? Cool, all right. Okay. So definitions, this is also honestly probably one of the weirdest and hardest part because there's so many different types of definitions. But basically, we start off with our population. This is everything. This is what we're basically trying to get approximations for. This is all of Canada. This is all of UBC, whatever it is, or all voting age people in a town. And then from there, we have a sampling frame. So this is like who we're able to reach. The accessible portion, so in this case, the database of registered voters that we can access. And then after we get that sampling frame, we take a sample from that sampling frame. So this is the people that do our survey. This is our sample, and we want it to be random. So in this case, we randomly select 500 people from our sampling frame. And a few things to keep in mind is you want your sampling frame to be representative of your population, and then your sample to be a random selection from your sampling frame for them all to basically, now you have your sample, and it's an accurate and it's a random, accurate depiction of your population. So that's kind of the 3 tiers. So you have your population, then you go to your sampling frame, and then from there, you pick your sample. Okay, so how do you pick your sample? So there's different methods. Simple random sample is, boom, completely random. No logic behind it, just randomly pick whatever. You reach your hand into a candy jar, mix it around, and it's good. Stratified random sample is basically you're choosing you have different groups, and then you randomly pick people from each of those different groups. Sorry, getting a call. Anyways, and then cluster is you divide it into groups, But instead of randomly picking people from those groups, you divide into groups, and then you pick an entirety of that group. So let's say if you divided professors by what they teach, you would be picking like all of the business profs. That would be a cluster. And then multi-stage is basically just repeating that, so multiple levels of it. And then systematic is, let's say if you want to pick out letters from the alphabet, you pick a random starting point, let's say D, and then you have a defined interval. So let's say now you're picking every third letter. So for systematic, you pick a random starting point, but then you have regular intervals where you're going from. Are there any questions with that? Yeah.
Could you just say stratified random?
Yeah, so basically, stratified random is, so you're dividing your sampling frame into groups, and then you're randomly, you go to a group and you're like, yo, let me randomly pick people from this group. Then you go to the next group, randomly pick. So for example, if it was provinces, you would divide the country into provinces. You go to one province, you randomly pick people. You go to another province, you randomly pick people. Versus cluster, it's like you divide into provinces, and then you pick randomly an entire province. So you're picking all of the group.
Okay, thank you.
Does that make sense? Okay. But now, okay, displaying data. Did I skip one? No, okay. Oh, there we go. Yes, I did. Okay, so what makes a good sampling or good data? What makes a bad sampling? What happens when it's not random? One is if it's voluntary. So if I just pull you and goes like, raise your hand if you like oranges. That's a bad sampling frame. I can't use that data. So it's basically you're letting people choose. So this is when people come up to you with like clipboards and asking for data. These are all, or social media. These are all examples of bad sampling. The next is convenience. So if I just go up to the people close to me like, hey, do you like mangoes? That's convenience. So another thing, you don't want to just go for the people who are closest or easiest to reach, because that's not representative of your population. And then sometimes you can have undercoverage through biases. So basically undercoverage means is a proportion or a part of your population isn't accurately reflected in your sample or sampling frame. And this happens due to a few biases, one of them being a non-response bias. So if someone is filling out your survey and they're like, nah, this sucks, they stop doing it, you have to keep track of that, and it's a non-response bias. But if every single person from a specific group was filling in your survey and they all stopped doing it, you would have undercoverage of that group. The second one is a response. So let's say you're hiring for an interview and you give a random survey of, do you like our company? Probably people are going to tailor the response to absolutely, I love your company, and not be more honest. So sometimes respondents can tailor their response to please the people running the survey. The last one is push-pull. So this is basically if I say, hey, did you know that car crashes are really bad? Do you think car crashes are really bad? Then odds are you're gonna be swayed in a certain direction. So this is providing information before you ask a question. And these can all affect the data. Okay, so basically a few different types of displaying data. One is frequency tables or relative frequency tables, basically using quantitative and quantitative. So basically here, it's just a few different ways. So you have kind of categorical data as a column, and you're saying, okay, in January, how many did I sold? That's your frequency, but it can also be a relative frequency. So in the middle one, you can see, okay, this is the actual frequency or the count, but then if you divide that by your total, so 5 divided by 20 is your relative frequency. Any questions on frequency tables? And from the homework, basically, for the most part, use column percentages. I didn't like that question, but yeah, for the most part, for relative frequencies, it's better to have column percentages. Okay, displaying data bar chart. This is for categorical data, or it can be also used for categorical and quantitative data, so comparing it. Key things to keep in mind, there are spaces, and that's pretty much it. You can graph it in Excel. Keep in mind of like where you're starting, so you're not misleading people by like trying to extend the differences between the charts. But yeah, it's mainly used for categorical data. Sometimes your y-axis can be a bit different. And then histogram, this is for quantitative data. So basically what you do is you take your quantitative data and you divide it into boxes and you smush them all together. And this is now a histogram, and it's for showing, you can see what type of skewed would this be? Right skewed, exactly. So you can see the skewness, you can see what like the mode would be, and it's basically dividing quantitative into boxes, and then there's underflow and overfill. So if you had an outlier, you could include that in an underflow box, and then also make sure, so it's from 0 to 10, that would be inclusive. So it's like if you have 10, that would go in the first box. So here, these are basically representations of histograms, and basically those little bumps that you can see, those are modes. So for a unimodal, that would have just one distinct mode or one distinct kind of peak per se, and then skewed to the left means that the tail goes to the left. Opposite, skewed to the right, means that the tail goes to the right, and the tail pulls the mean away from the median. So what the mean is that's like whenever you think of average, that's what it is. It's all of your data added up and divided by, essentially, like the number is basically giving you an average, but the median is basically the middle point of all your data sets. So 50% of your data is above the median and 50% is below. So for a skewed data, because there's a bunch of small datas in one direction, it pulls that average towards it. So if it's skewed, the mean and the median aren't aligned, versus for a normal, they're together. Outliers are basically just something that is different, or if there's a specific pattern. So here you can see it's a normal distribution, and then there's a other deviation. Uniform, this uniform distribution is basically there's no significant change throughout it, and then sometimes it's just completely random. And then another way of graphing these are called box plots. So this is another way for graphing quantitative data as a side from histograms, and they're really good for comparing different quantitative data. So the few things to keep in mind, we already talked about the mean and the median. Sometimes the mean and the median. The median is the line. Sometimes they put the mean in, but sometimes they don't. And then what you have here is Q1 and Q3, which is your first quartile and your third quartile. So that's like 25th percentile and 75th percentile of what your data is in. And then these whiskers are essentially where the last point of your data is before the boundary. So the boundary is basically just used to show where an outlier is. So there's an invisible line that you can't see, which is for the upper boundary. It is Q3 plus 1.5 times the IQR, which is the interquartile range, which what that is just Q3 minus Q1. And we'll get to that, but basically it's an invisible line, and then wherever the last data point is below that line, that's where you draw the whisker. So you can't actually see the boundary unless it lies exactly on that data point. So this is kind of what we were talking about, and these are the functions in Excel. For normal distributed data, you want to use the mean and the standard deviation, which is just a measure of the variance. Essentially, it's the square root of the variance. And then for skewed data, you want to use the median and the interquartile range. This is just giving you a better depiction for data analysis. So for skewed data, there's the median and the interquartile range, and that's because for skewed data, again, the mean is pulled towards the tail, but then for normal, you can use the mean and the standard deviation. There's some more formulas. There's some more formulas here. So the max, that's just your highest point. The min is your lowest point. And then this is what I was talking about for the upper and lower boundary. Basically just invisible lines of where we classify outliers to be, whether they're above that or below that. Variance, basically, there's the different formulas for variance for a population and a variance for a sample. So it's basically a representation of how much the population data deviates from the mean. So in its formula, you basically take that point minus the mean and then divided by the amount, and you sum all those together, but basically all it is represented is like the variability of it. So if you were to randomly pick something from the population, that's essentially what variance is. It's just the variability of the population. And for binomial data, what binomial data is basically if you have an event with a chance of success or failure, it's called a Bernoulli trial. And all binomial data is a combination of a bunch of events of Bernoulli trials. So it's a bunch of events put together where there's a possibility of success and failure. The possibility of success is Q, the possibility of failure, the probability of success is P, the probability of failure is Q, which is 1 minus P, and the variance for binomial data is a simple expression. It's just NP times Q. And then the difference is, now that was for a population, but then for a sample, this is basically, we're trying to calculate how much this sample's mean deviates from the population. So there's a different formula for the sample variance, which means that there's a different formula for the standard deviation variance. And I think that's one of the more important things to keep in mind. There's a thing with degrees of freedom, which I don't think we have to worry about, but basically all it's saying is that like you're correcting for estimating the mean of the population. But okay, so this is how I like to think about how we get to the formula for sample variance, which is the primary one that we use. So if we have an event and X is the number of successes and N is the number of trials, our P hat, which is basically if we take a sample, that's the proportion of successes that we have of our sample, would be X divided by N. And then we also know the formula for variance. If a variance times a number, variance of a variable times a number equals the variance of that number, variance of the variable times that number squared. So we're basically just doing some algebra on the right side. So for the variance of the P hat, it's the same thing as the variance of that variable divided by N, and then we take out N, and then it would have to be squared, so it would be 1 over N squared. And then as we saw before, the formula for variance of a population is NPQ, and now we're dividing that by N squared. So we're left with PQ over N as our formula for variance. And then if we take the square root of that, we have our standard deviation formula for the sample, which would be square root of PQ over N, and that would be for our sampling distribution. We're moving on to z-scores and z-values. I think these are pretty important, but basically all you're doing is you're trying to come up with a way to compare different data and make it easier, I think, to visualize and to understand. And all it's showing is how many standard deviations from the mean a value is. So a z-score of 3 would mean that that value is 3 standard deviations away from the mean. A z-score of -2 would mean that it's -2 standard deviations. And the way we get there is we take the data point minus the mean, and then you divide that by the standard deviation. You can calculate this in Excel, and this means that you're standardizing something. So if you get z-scores, then you'll use .s function. So that's for norm.s dist and norm.s inv. And the one thing to keep in mind is when we get to later, the mean will almost always, the mean of the population will be approximated with the mean of the sample. But the thing to keep in mind is that when we're dealing with sampling distributions, the standard deviation of the population is different than the standard deviation of the sampling mean. So when you're doing this calculations or any calculations where you're having standard deviations, know whether or not it's for the standard deviation of the population itself, or there'll be use the formula for the standard deviation of the sampling distribution. And we'll get to that. A few properties of it. One is unitless. So if you change units within your values, it does not change the z-score at all. If you take the mean of all z-scores, it'll be 0, and the standard deviation. And again, when we say to standardize something, it means to turn the data into their z-scores. Okay, so just really quickly, we're going to go over some quick scatterplot stuff. So the first thing when you're analyzing data for a scatterplot is to look at the relationship. So this is whether or not the slope, it's a positive or a negative relationship. So does y increase or decrease as x increases? Once you've determined that, what form is it in? In this class, we're mainly only dealing with linear. So if it looks like a line, probably is a line. If it doesn't, it's not. And there's other forms of relationships like exponential and others, but we're not really going to worry about that. And then after you've determined the type, hopefully it's linear, and then you can look at how strong the correlation is. So are they pretty random, or is there a pretty strong pattern? And then you can look at anything else, so any outliers, weird trends. And one thing to note, this is only for 2 quantitative variables. So if they try to trick you with, categorical and scatterplot, categorical and quantitative, you can't do it. So this is only for 2 quantitative variables, and keep that in mind for the next few slides that we go to. All right, so linear regression. Basically, what we're doing is we're using Excel to create a line of best fit which minimizes the sum of the squared residuals. What is the residual? We take the actual y point, y, and we minus the predicted y point, y hat, and that gives us our residual. It can be positive or negative. We square them, and we add them all up, and whichever line, whichever slope and intercept of line gives us the minimum square root of residuals is the one that we use. This is the line of best fit. And the mean of residuals is always 0 for the line of best fit, just like z-scores. An important thing to keep in mind is that we can't extrapolate further than the data that we're given. Even if the line could continue, you can continue the slope, it doesn't mean that you can predict those y values because it's out of the scope and out of the range of the data that you are given. And what that this line of best fit does is it predicts y based on an x value. So you go to an x value and then it predicts what y should be there. In Excel, you do this through going to data analysis, by going to data and then data analysis, and you can find all the residuals. You can plot the residual spread, which what you want to have is an equal residual spread. This means that your line of best fit is good because you want a random distribution basically of your residuals. So they can't be following a trend. They can't be super close together to the center line there and then spread out further there. You want them to be random throughout at a constant level. That means that your line of best fit is good to go. And in order to do some error correcting or just correction for rounding errors, sometimes it's important to just use equal correl or equal slope or equal intercept in order to find a more precise value that you can copy over into your answers, as opposed to just relying on what the graph of the line of best fit actually gives you. Okay, so now we're looking at the strength of the relationship. So this is called the correlation coefficient, denoted as R, and it's basically just measuring the strength of the correlation. It has to be between -1 and 1. -1 is a perfectly negative correlation, 0 is no correlation, and then 1 is a perfectly positive correlation. So that's just perfectly positive, x increases, y increases. And another properties of it, same, it's unitless. So again, if you're changing the units of anything, it does not affect the R score. So there's the formula that you can calculate in Excel, which is really complicated using the z-scores, or you can just equal correl and then put in your 2 columns of data. That's pretty simple, and the order does not matter. So if you put in equals correl y column, x column, or x column, y column, it's the same thing. The order does not affect it, and just keep in mind that it's between -1 and 1, okay? And then another kind of thing to keep in mind is R squared. So this is similar to R, but it's a little different. This is essentially, it shows how good your model is. So what your R squared value is it's the percent of y that's predicted by x. I think that's the best way of thinking about it. So it's like if your R squared value was 0.8, 80% of y can be predicted by x. And because it's squared, its value has to be between 0 and 1. And a higher value of R squared normally indicates a better model, but not always. So make sure if it always says, oh, an R squared was always better, that's not necessarily true. Now, I'm probably heard about the sharks. More ice cream sales equals more shark attacks. So causation versus correlation. So X can predict Y, but that doesn't necessarily mean that X causes Y. So just because X can be a predictor for Y, that doesn't mean that it causes it. So just because as ice cream sales increase, we can predict that shark attacks will increase, doesn't mean that it causes it. We have to look for lurking variables such as warm weather or weather. Does that make sense? So just because it can predict it doesn't mean that it can cause it. Quick randomness explanation. So the expected value for when we're dealing with kind of that Bernoulli trial, it's essentially the same thing as the mean. We just take our number of trials multiplied by the probability of success. If 2 things are mutually exclusive, then they're dependent to events, because if one event happens, you know the other event can't happen. So mutually exclusive means, or indicates dependent between 2 events. And for independence, just think that if one event happening, does that affect the probability of the other event happening? And then basically for randomness, there's discrete, which is basically able to be countable, and then continuous, which has an infinite number. It can basically be like super specific, super specific numbers. And what we were kind of talking about before between Bernoulli and binomial. Bernoulli is just a single event with 2 possible outcomes, success or failure. Binomial is a combination of all of those. So this brings us to the central limit theorem, which I'm going to do my best to explain, but the few requirements for the central limit theorem to hold is we need a random sample. So that's, how do we get that? From what we were talking about before. And then the next thing is we need, so NP has to be greater than 10, and NQ also has to be greater than 10. And then the last thing is it, for the most part, can't be greater than your N, your sample size, can't be greater than 10% of the population. So those requirements keep in mind. Basically for everything else that we're going to do today, just remember that. And P is the population. So basically, what we're trying to do is we're trying to estimate how the sample relates to the population. So we're doing this through a sample distribution. So basically, we're trying to estimate how the taken sample will behave. So if we took one sample, and then we took another sample, and then we took another sample, and then we took the average of all of those samples, the odds are that the mean of all of those samples would be the same as the mean of the population. So that's the one important aspect, which means that the center of the distribution is going to be the mean of the population. So what we do is essentially we assume, or it's been proven that as n increases, which is this like NP greater than 10, NQ greater than 10, as it increases, if it's large enough, these distributions will behave like a normal distribution. So what a normal distribution is, we'll get to that, but basically is if these conditions are satisfied, then the sampling distribution will behave like a normal distribution, and its mean will be the mean of the population. So the center of the sample distribution, the sampling distribution, will be the mean of the population. And then that's where the mean of the sample is approximated to the mean of the population. But then the standard deviation for the sampling distribution is not the same. So you want to take the standard deviation of the population and divide it by the square root of the number of, by n, the number of events in this data. So you can use the same mean as the population for your sampling distribution, but the standard deviation is the standard deviation of the population divided by the square root of n. So when you're doing your norm.dist for a sample, you want to use this mean, and then you want to use that sampling mean standard deviation. Are there any questions about that? Okay. And we use this to basically find the probability that something is less than a specific point on that standard deviation, or the inverse of that, so where a specific point of probability lies. Really quick, just going over a few formulas. If we're adding together expected values or means, we can just add them right together. If we're adding or minusing variances, we can add them together, but it's always addition. So if you have variance of x minus y, it just equals variance of x plus variance of y. We cannot add standard deviation, so you have to square them to get the variances, and then add them together, and then take the square root. So you can't just add plain standard deviations. And then just other things to keep in mind is if you add a constant to a variance, it doesn't affect its variability, so you just get rid of it. And the last thing, just a quick reminder with probability. The probability of two events happening, so let's say x and y is the probability of x happening, plus the probability of y happening, minus the probability of them both happening, to avoid double counting. Okay, so this is what we were talking about for normal distribution. So what does the norm.dist function actually do? So you input x, and what that is just a value that you give it. So for this one, that's where that line is. And then what the function is giving you is the area under the curve to the left of it. And that's the probability. So you input x, then you input the mean, which is the middle, and then you input the standard deviation, which is the distance from the green to the one of the dotted lines. And then what it will give you is it will give you the probability to the left of that x value. So everything to the left of that x value that you input is giving you everything to the left of that. So that's like the probability to the left of that. Are there any questions with the norm.dist function? Okay, and the inverse of the norm.dist function, what you give it is its probability, and then it gives you the x. So for norm.dist, you give it an x value, you give it kind of a position on your graph, and then it gives you a probability. For norm.inv, inverse, you give it a probability, and it gives you back an x value. But basically, it's the 68, 95, 90.7 rule, 99.7 rule. So 68% of your data will fall within one standard deviation of the mean, so -1 or +1. And basically, I divided it up, so then if you ask a question like, oh, what percentage of the data would fall between -2 and 1 standard deviations, you can just add up those numbers, so like 13.5, 34, and 34. You can just add those all up to answer this question. And then just remember, yeah, it's just split up evenly because it's a normal and symmetric distribution. Okay, so then now what happens if we standardize something? Now we're using the norm.sdist function. So now, because we've standardized it, we don't need to input the mean or the standard deviation, because when we standardize something, the mean is 0 and the standard deviation is 1. So this function just assumes that that is the case. So we input the x value, what we're looking for to the left of, and it gives us the probability to the left of that. We're looking for less than, let's say less than a specific value, so what percent of students are less than a specific value, we'll use the actual function. But then if we want more than, greater than, we're going to use 1 minus norm.dist. So greater than, we want to use 1 minus that, because the function gives everything to the left. So it's like what percentage of students are over a height of 2 meters. That'll be to the right, so 1 minus that. And then over here is just going quickly through an example for a type of problem where you're wanting to find, like let's say we're playing golf and you're wanting to find the probability of someone beating someone else. So that would be of something being smaller than something else, so x being smaller than y. And the best way to approach this problem is with the formula. So your means you can just subtract. So we have the mean of 110 minus the mean of 100. That'll just give us a combined mean of 10. But then remember, for standard deviation, we have to do the separate thing where we square it, add the variances, and then take the square root. And then once we have that, we can just put it in. And basically, in the bottom here, the 0, where is that coming from? That's coming from the probability of x minus y being less than 0. So that's where that 0 is coming from. And then we subtract the combination means, and we divide it by the standard deviation, which we calculated with the squared standard deviations added together, square rooted. And then that gave us a number, and then all we did is we plugged that into Excel with the norm.s.dist function to give us a probability. Are there any questions with that? So you're using the combined mean, because you can just add them, you can just subtract them, but then you're using the standard deviation, which has a little bit more complicated formula to go against, and then you take whatever the value is for like greater than or less than 2, and then you're minusing that combined mean, and then plugging that into Excel. Okay, so then for confidence intervals, we're going to start off, you want to assume that the center of distribution is essentially the mean of the center of the normal distribution is p hat. So you're assuming that from your sample that you collect, you're assuming that the center is the proportion that you got. So if you sampled people and 50% said they like oranges, you're assuming that that is your center. And then now you choose a confidence level. And the best way I like to think about this is, let's say we're looking for a confidence level for 85%. We want to be 85% confident, which means we capture 85% of the true population. What we do is we take that 85% and then we do 1 minus 85%, so that'll give us 0.15, and then we split it off into the two tails. So that's why there's 7.5 and 7.5. You take that 0.15 and you split it into the two ends, and then using Excel, you're using the function norm.s.inv of that value. So 1 minus whatever is in that right tail, 7.5, is going to be your z star. So 1 minus 7.5 is your z star, or 0.075, and then in the function, you put in norm.s.inv of that value. So you split it off into two tails, you take your right tail, 1 minus that, and you put that into the norm.s.inv function. That gives you one part for your confidence interval, and then next part, you have to calculate your standard deviation, or standard error, which is essentially just an estimate of the standard deviation of the population. So you use p hat and q hat, which is basically what you got, so your proportion of successes from your sample. And you divide that by n square rooted. That's just the formula we did before. And then to get to your margin of error you multiply your z star, which is what we calculated with the norm.s.inf function, times your standard error, and then your final answer will be your mean, which is the center of your distribution, p hat, plus or minus your margin of error. So you start off with your mean, then you get your confidence level, you pick it, let's say it's 85%. You figure out what your z star would be by using norm.s.inf function, and then you multiply that by your standard error, which you calculate using p hat, which is the proportion you got from your sample, q hat, n, do all of that, and then you add and subtract it to give you your final answer. Are there any questions with that? Okay, and then your upper bound is just basically your highest value of your range and your lowest value range. And again, this confidence interval will give you, it captures 85% of the true value of the population if we have a confidence level of 0.85. Sorry, okay, and then here's just a quick example of some critical values. So basically what we did for this one, you either can just memorize it, or again, so for 90%, you split 5% here, 5% here. 1 minus 5% is 0.95, so norm.s.inf of 0.95 will give you that value. So if there's a question that asks you for some reason like 88 confidence level, you can take it, so that'd be 12, split, 1 minus 6, and then plug that into your value. And that way you don't have to memorize this and you can think about it a better way. So if you have a smaller or narrower margin of error, you'll have lower confidence, but you'll have more precision. If you have a lower confidence level, obviously you'll have lower confidence. And then if you change n, so let's say you increase n in order to kind of decrease the margin of error. You increase n, it decreases the margin of error by square root of that. So if you increase n by 9, it'll decrease the margin of error by 3, because in the formula, we're square rooting n. And then if you have a larger n, you will have a smaller margin of error because it's divided by it. You'll have more precision, so you want a larger n to give you more precision, and it will basically give you the same level of confidence, but with a narrower margin of error. So you could get a 95% confidence level without having such a wide margin of error. It can be narrower. If you have a super wide interval, you'll have a higher margin of error, and you'll have higher confidence just because it's basically casting a big net, but it might not be super precise. And again, keep in mind the conditions for all this to be true from the central limit theorem. These are just rearranging the formula we did. So let's say you have a margin of error that you want, and you want to find what size of sample do we want. This is the formula. You plug in your margin of error, 1 over that squared. That'll approximately give you what size of sample you would have. And then this one is, let's say you're given the sample size and you're given the margin of error, and you want to determine what confidence level that is basically kind of the inverse of what we did. So you take your upper bound, which is p hat plus your margin of error, and then you minus p hat. That'll give you your margin of error. And then to get your z star, basically you take that margin of error and you divide it by your standard error, which is the formula that we've done before. And then once you have that z star, take the absolute value of it, take the negative of that, put it into norm.s.dist true, and multiply that by 2, and that'll give you your confidence level. So once you calculate your z star, which is again your margin of error, which is what you're plus or minusing from your mean, divided by your standard error, take the absolute value of it, you want it to be negative. So take the absolute value and then multiply by -1 to give it negative, and then once you've done all that, times it by 2, that'll give you what confidence level. This is in case it comes up, I think it's important. Okay, hypothesis test. Basically, it's used to test whether or not let's say, people say, oh, Dell computers are 90% fast, or whatever. You're proving you're proving the probability of a population if it's accurate through testing with a sample. So you start off with a null hypothesis. This is something that is not changing. So if someone tells you, hey, 90% of people like mangoes, that is your null hypothesis. So it'd be H0, your null hypothesis, equals 0.9. So that's something that's not changed. And in this class, we only do it with equal signs. So there's no less than or greater than for null hypothesis. And then the other hypothesis is any other possibility. So it'd be any other possibility either does not equal sign, or if you're only looking for greater than or less than. So let's say hey, I want to see if more than 90% of people like mangoes, then you would use a one-sided hypothesis test. So two-sided is not equals, one-sided is greater than or less than, and that just matters whether or not you times it by 2. So what we are doing is we're calculating a p-value and we're comparing it to alpha. So p-value is the probability of getting your sample proportion, your p-hat, assuming that the null hypothesis is true. So if I do a sample of people and I'm trying to find whether or not 90% of people like mangoes, it is the probability of me getting, let's say, 60%. From my sample, 60% of people like mangoes. It is the probability of me getting 60%, assuming that the population actually likes 90% of mangoes. Does that make sense? Okay, and then in order to reject the null hypothesis, so this is basically saying this is such a small probability that it would actually not happen. It's statistically insignificant. It has to be either equal to or less than your alpha value, which is just a set value. Normally it's 0.05. Sometimes it could be 0.01. But basically, if your p-value is equal to or less than that, you can reject the null hypothesis. And in order to do this, again, central limit theorem requirements must be true. You'll have to know the given parameter, so that's your 90% of people like mangoes. You'll have to know how many people you surveyed, and that's your sample, and also your sample statistic. So in this case, it would be 60%. And then you're calculating the standard deviation with the p, which is your parameter, because you're assuming it is true. And we'll get to that. Okay, so you start off, first step, you have your null hypothesis, which is coming from the population. Your sample statistic is your p-hat. Second thing, you want to calculate the standard deviation. You're doing this with your population proportion, so not what you got. So I got 0.6, I'm not using that, I'm using 0.9. So it'd be 0.9 times 0.1, and you divide that by how many people you surveyed, n, and you take the square root of that. And then now we put that into a little formula, so that is, so we take that, what we calculated, so that'd be 0.6 minus the mean, or the proportion of the population. So in this case, it would be 0.9. And we divide that by the standard deviation we just calculated. And this essentially gives us a z-score. And to make our lives easier, once we calculate this, we're going to absolute value it once again and times it by -1. So once we've calculated, so we take our 0.6, the proportion we got from our sample, minus the proportion of the population that was given to us, divide it by the standard deviation. That gives us z. We're going to turn that into absolute value and make it negative. And then all we have to do is just plug it into norm.s.dist, plug that in, and then if it's one-sided, do nothing. If it's two-sided, times it by 2. And then compare it to your alpha value. So once you've done all that, the last step is to reject the null hypothesis if it is equal to or less than. But the important thing to keep in mind is if it's greater than alpha, so let's say it's greater than 0.05, it does not mean that the null hypothesis is true. It just means that you're unable to reject it. So if there's a question that says, oh, because your alpha level was 0.9, does this mean the null hypothesis is true? That's not the case. You don't know for certain. All you're able to do is just not reject it. There's not enough evidence that it was random. And then just a few extra notes. Sometimes for notation, it'll be like this, n01, which just means it's normal distribution. The 0 mean and 1 is the standard deviation. So that's for z-scores or for anything else. And then once again, remember, for samples, standard deviation. So the standard deviation for population is just the square root of n times p times q. But then your standard error, for a sample, is basically p hat, q hat over n all square rooted. And that's derived from the formula that we went through. And then q is just 1 minus p. This is chance of failure. For basically all questions, for norm.dist, use true. And then your null hypothesis is no change. So it's not something that you're changing. It's like, oh, I wonder if the population likes, 65% of the population likes mangoes, or let's see if it's 68. There's no change for the null hypothesis, and you can't prove it's true. And then the last thing to keep in mind is that all the functions norm.dist and norm.inv are to the left Beyonce functions. That's it. Yeah, thank you. I'll pause that. I know it was a bit rushed. If you're looking to get involved, we're looking for graphic designers. And also, please, we would really appreciate your feedback. So if you could take a little bit of time, fill in the form. Our goal is just to helps us study, hopefully helps you guys study with the courses. So if there's anything we can do to make these better, help you out as best we can, that would be awesome. So please, if you have 30 seconds, just fill out the feedback form. We would greatly appreciate that. You can take photos of that. And all these slides and stuff will be posted and everything. But yeah, so thank you everyone so much. This will be posted up on YouTube at UBC Simplified. We have an Instagram account you should follow because that'd be really cool. And yeah, thank you all so much for coming.